All right, Unit 5 is the beginning of our unit on linear programming. And here's the type of problem that we'll be able to solve by the end of this unit in a couple of weeks. So this is about cooking. Baking a tray of corn muffins takes 4 cups of milk and 3 cups of wheat flour. A tray of bran muffins takes 2 cups of milk and 3 cups of wheat flour. A baker has 16 cups of milk and 15 cups of wheat flour. He makes $3 profit per tray of corn muffins and $2 profit per tray of bran muffins. How many trays of each type of muffin should the baker make to maximize his profit? What we're going to do in a problem like this is we're going to try to figure out what are the different combinations of the unknown, in other words, the number of trays of corn muffins and the number of trays of bran muffins that are actually possible in this situation, where he's using the correct amounts of milk and wheat flour to make his muffins while staying in the constraints of having 16 cups of milk and 15 cups of wheat flour to work with. And knowing that we have different combinations that are possible, we also want to know which combination is going to give him the most profit, because that's how he's going to make money. So we're not actually going to solve this problem right now, but this is something that we'll look at over the course of the next 3 or 4 lessons, where we'll kind of look at one piece at a time. So this is our plan for this unit. So starting today, our day 1 lesson is going to be focused on writing systems of inequalities. So in a problem like the one that we just saw, we are going to need to write several inequalities that make up that problem and that go together or fit together. In our next lesson, we'll look at graphing that system of inequalities so we can get a visual representation of what it looks like and what the solutions look like. On day 3, we're going to find what's called the vertices and the feasible region. And then in day 4, we'll write and use an objective function to help us make a decision based on the situation. In day 5, we'll review all 4 of the previous days by looking at application problems or real life problems where we go from beginning to end and apply everything that we've learned. We'll finish with our unit assessment before the end of the semester. So here's the beginning of our day 1 lesson for unit 5, writing a system of inequalities. So let's start with a few definitions. What is a system of inequalities? Well, a system of inequalities is when you have 2 or more linear inequalities that describe a relationship between 2 variables. For example, we have y is less than 3x minus 1. We also have that 2 times x has to be greater than or equal to 12, and that y has to be greater than 0. When you put all 3 of these together under the same situation, it becomes a system of inequalities and not 3 individual inequalities. So what are solutions to a problem like this? Well, solutions would include any ordered pair, so any x and y value that satisfies each linear inequality in the system. For example, if I find an x value that when I multiply it by 2, it makes it greater than or equal to 12, I also have a y value that's greater than 0, and when I use that same x and y value, I get that the y value is less than 3 times the x value minus 4. That would represent a solution. But the x and y has to work in all 3 of these inequalities. Otherwise, it's not a solution to the entire system. Problem number 1 reads, at Brantley's Bakery, a batch of cookies requires 2 cups of flour and 25 minutes to bake. A cake requires 3 cups of flour and 45 minutes to bake. Brantley has budgeted for 27 cups of flour per day, and he can bake for only 450 minutes per day. Write a system of inequalities to show how many batches of cookies and how many batches of cakes Brantley's Bakery can make. Determine what the variables are and give a system of equations to fit the situation. And actually, that should read a system of inequalities to fit the situation. So the first thing we're going to do is we're going to create and complete this graphic organizer that's going to help us write our inequalities. So what we have here is the very first item is our variables. Variables are the unknowns, the two things that we don't know. Usually you can find those in the description for or either a question or it describes what you're supposed to do. Again, we're looking for unknowns. What don't we know about the situation? It says to write a system of inequalities to show how many batches of cookies and how many cakes Brantley's Bakery can make. So those are the two things that we don't know. The number of batches of cookies and the number of cakes. Those are our variables. What I'm going to do is I'm just going to label those in the same order that they appeared. The first one will be the first variable, or x. So instead of saying how many batches, I'm going to just say number of cookie batches. Okay, so not number of cookies, but number of cookie batches. So 5 batches, 6 batches, and so on. Because each batch might have 4 dozen cookies in it, not just one cookie. Then the y value is going to be the number of cakes. Now, the other things that we know about these, each batch of cookies or each cake, is the amount of flour and the amount of time required to bake each one. So in my graphic organizer, I put my variables on the top, and then I put the other quantities down the side. And now I want to fill in the boxes. So for batch of cookies will be the first column. How many cups of flour are needed for one batch of cookies? And up above, it says a batch of cookies requires 2 cups of flour. So I'm going to put a 2 in that first box. And then below that would be the amount of time required for a batch of cookies. I'm just lining it up like a multiplication table. And it said a batch of cookies was 75 minutes to bake the entire batch. A cake requires 3 cups of flour and 45 minutes to bake. So underneath the cakes, we're going to require 3 cups of flour and record 45 minutes to bake. You know, while I'm here, I'm also going to label my variables. That batches of cookies was X and cakes were Y. Now there's a little bit more information that we know that we did not necessarily use yet. Give me 1 second to highlight. 2 cups of flour, 75 minutes to bake, 3 cups of flour, 45 minutes to bake. Then in the next sentence, it says Brantley has budgeted for 27 cups of flour per day. That's like a total amount that he can use, up to 27 cups of flour. Now, it's possible that he doesn't use the entire 27 cups of flour, and it certainly is possible that he uses all of it, but what he can't do is use more than that. So under the row for flour, we know it's 2 cups for every X, it's 3 cups for every Y, and we also know that Brantley has to use less than or equal to 27 total cups of flour. So see how I line this all up in the same row? Okay, so 2X and 3Y has to be less than or equal to 27 total cups because he can't use more flour than what he has. Now let's look at the constraint or a limit on the amount of time that Brantley has. It said that Brantley can bake for only 450 minutes per day. That's a constraint on how much time he has available. So if it takes him 75 minutes to bake a batch of cookies and 45 minutes for every cake, we know that he can use less than 450 minutes of baking time. It just means that he doesn't use it all. Or he could use all of the 450 minutes of baking time. What he can't do is use more than that. So we're going to use less than or equal to 450 as our constraint. So for writing our inequalities, our graphic organizer basically has everything set up for us, except for putting the variables in place. So remember, the batches of cookies are X, the number of cakes are Y. So we're going to take 2 times X, and we're going to take 3 times Y for the cakes. And when we add those together to get the total amount of flour that Brantley uses, it has to be less than or equal to 27 total cups. Okay, this is the constraint on flour. The second inequality comes from the second row of our table. It's really a constraint or an inequality on the amount of time that he has. It takes 75 minutes for every batch of cookies. It takes 45 minutes for every cake. And when you add that together, you get a total amount of time that Brantley uses. Well, the constraint on time is that Brantley only has 450 minutes in that day to bake, so it has to be less than or equal to 450 minutes. Just going to label that as a constraint on time. Finally, we have 2 more empty rows here, and you might be wondering, well, what are those for? Our graphic organizer doesn't have any more space here. And the last 2 rows are really just constraints in general, okay? Constraints on our variables. And it has more to do with just what makes logical sense in real life. Now, X is our variable that represents the number of batches of cookies. So let's think about, can X be any number possible? Well, no. I mean, we know that there's a limit based on the amount of flour and time that he has, but even what makes, I guess, more real life sense is that X has to be a non-negative number. Think about that. Can you make -3 batches of cookies? No. Can you make -10 batches of cookies? No. Can you make 0 batches of cookies? Yes. Could he make 5 batches of cookies? Yes. But the only thing that's really not possible are negative numbers here. So one more inequality for the batches of cookies is to show that X cannot be negative. In other words, X either has to be greater than 0 or equal to 0. So our inequality is X is greater than or equal to 0. And that's going to be our constraint for the batches of cookies. Then the last one is going to be very similar to that, and that's based on the number of cakes. For the same reason that you couldn't have a negative number of batches of cookies, you can't make a negative number of cakes either. So Y has to be greater than or equal to 0 as well. So what we end up with is we really end up with one constraint or inequality based on each of these 4 items listed in the graphic organizer. Okay, for the flour, we just went left to right using everything we had from our paragraph. For time, we went left to right based on everything we had in our paragraph. But then we could also write an inequality about each individual variable, saying that X has to be either equal to 0 or bigger than 0. It's basically just saying it has to be a positive number or it could be 0. X just can't be negative. And we do the same thing with Y. Now this is going to be pretty similar for almost every problem we do, and it might be for every problem that we do. And it's just saying in real life, your unknown quantities are very rarely going to be negative. So if you need to, take a moment to copy that down, and then we're going to go on to number 2. All right, with number 2, we have the BHS Pizza Kitchen, specializing in individual pizzas. The Sparky Pizza has 4 ounces of cheese and 16 ounces of pepperoni. The Blaze Pizza has 5 ounces of cheese and 9 ounces of pepperoni. The kitchen purchases 600 ounces of cheese and 1,440 ounces of pepperoni each week. Determine what the variables are and write a system of inequalities to fit the situation. So in this case, they didn't give us the labels to work with. We do know that we want X and Y, or our unknowns, to be on the top, and we want some of the quantities that we already know some things about to be on the side. Now, it doesn't necessarily say to write a system of inequalities for this and for that. Okay, so it doesn't really give us that straight up, here's the unknowns. So we have to do a little bit deeper dive. So what do we know and what do we not know? Well, let's see. Do we know how much cheese we need? Well, I guess kind of. We know how much cheese is used on a Sparky pizza. We know how much cheese is used on a Blaze pizza. We know how much cheese the kitchen purchases or has to work with. So cheese is going to be one of those things that goes on the side because we know a lot of that information. And it may even help to try to organize some of this right away. So cheese, well, what did we know about cheese? We knew, and this is in ounces, we knew it was 4 ounces for one pizza type, and we knew it was 5 ounces for the other pizza type, and we knew that we had a total of 600 ounces in the kitchen to work with. Let's see, what was the other topping? Because these are toppings over here, as we can tell now. Pepperoni was the other topping. So pepperoni, sorry about my sloppy writing there. And that was also given to us in ounces. So let's see, this first one here was from the Sparky Pizza. 4 ounces of cheese, 16 ounces of pepperoni. So it looks like one of our variables is going to be the number of Sparky pizzas that the kitchen can make. So that's going to make our other variable the number of Blaze pizzas. Well, let's finish our table here. What we don't know is Blaze pizzas pepperoni. Okay, let's see. The Blaze pizza had 5 ounces of cheese, which we already put that in there, and 9 ounces of pepperoni. There we go. All right, so the cheese, the kitchen had 600 ounces to work with. For pepperoni, the kitchen has 1,440 ounces to work with. All right, so put yourself in this situation. You have these massive quantities of cheese and pepperoni in the refrigerator. Okay, if you have 600 ounces of cheese, can you use less than that? Sure, it's okay to have extra. Could you use all of it, or exactly 600 ounces of cheese? Yes, you'd use it all up. Could you use more than 600 ounces of cheese? No. So I ask these questions because it helps us decide which inequality symbol to use here. The amount of cheese for the 2 pizza types has to be less than or equal to 600 total ounces of cheese. And for the same reason, the pepperoni is going to be the same thing. Okay, the amount of pepperoni is less than or equal to 1,440 total ounces because that's what the kitchen has available. If you feel like you want to try this, why don't you go ahead and pause the video and try to write your inequalities for the system down below. And there should be 4 total inequalities when you're done. If you don't feel like you're ready, just watch and listen. So we're going to write an inequality starting with cheese. we knew that it was 4 ounces for every Sparky pizza. So we can use 4 times X to represent that total amount. We also knew that it was 5 ounces of cheese for every Blaze pizza. So we can use 5 times Y to represent that total amount. When we add those quantities together, we get a total amount of cheese used by the BHS Pizza Kitchen. And we also know that the constraint was the limit on the amount of cheese, right? You can only use the amount of cheese that you have. You can't use more than that. So we have that limit of 600 ounces of cheese. Let's write a similar inequality for pepperonis. It's 16 ounces for every Sparky, and it's 9 ounces for every Blaze pizza, and the limit is 1,440 ounces of pepperoni. Now the last two inequalities are for X and for Y. X is the number of Sparky pizzas, and the BHS Pizza Kitchen could make 0 Sparky pizzas, or 1 Sparky pizza, or 2 Sparky pizzas, or 3 Sparky pizzas, and so on. What they can't do is make a negative number. So just like in the last example, we want to say that X has to be greater than 0 or equal to 0 to show that X can't be a negative number. And then the same thing for Y. Y also has to be greater than or equal to 0. So there's our limit or our constraint on the Sparky pizzas and the Blaze pizzas. And that makes our system of inequalities. What we're going to do in the next lesson is we're actually going to graph these systems of inequalities so that we can get an idea of what are the possible solutions to something like this. So that'll come in a future lesson.